when you straight away talk about light emitting diode, this is probably one of the most widely explored diode that we have, and we have been using it almost on a very much on a daily basis, right? So any kind of indicators that we have usually are all nothing but made up out of a light emitting diode. Okay? So light emitting diode can be basically a very good signal to know whether a circuit is on or off. And an important thing that we should know that this light emitting diode is always working in forward bias. The reason is we actually need some voltage, a good amount of current to flow through the system so that we can actually get some current output out of it. Okay? So in this process, what we are going to see is that the first thing is very important, the symbol. Okay, and I think symbol is already known to most of us because this is more or less mm, uh, similar to a normal PN junction diode, except this part, right? Except the two arrows that are coming out. So please make sure that when you draw your symbol, you show it as two arrows which are coming out. Because if it is coming out, that means it is giving light. And if it is going in, means we are talking about photodiode. Okay. So anyway, we are not discussing photodiode in the syllabus. And when we look into the practical device, we have the anode and the cathode. Okay. And if you take up any diode, it becomes a bit difficult to know which one is the positive terminal and the negative terminal if you don't know the convention. Because whenever it's a diode, one side is the anode and the other side is the cathode. So anode or the positive side is usually the longer length, okay? And whichever is the shorter length is the cathode, okay? So whenever you actually take up any diode, it's available in the market for around 2-3 rupees, okay? Different color diodes are available and all of them are more or less in similar price range. Okay, so nowadays any lighting devices which is actually using diode is more or less cheaper, okay, much cheaper in cost. In fact, your televisions and all, you get a larger size, okay, with lesser power consumption. I think the credit goes to the use of light emitting diodes, okay. So diodes typically does not use elements like silicon or germanium, okay, that we know, because the property is kind of different that we need to explore. We wanted to actually give out some kind of light in the visible range, okay. So most of the elements that are used for diode are gallium. Okay, I can take gallium, and we can talk about phosphorus. Okay, so these are some additional ideas that you should have, and also arsenic. Okay. So these three elements actually comprises most of the diodes that we actually see around. Okay, and their combination. So depending on what are combined and how are these combined, okay, varying the quantity, we can actually know that what is basically the color of the diode that we are talking about, okay. So varying the amount, okay, we can say varying the quantities of this element. I think this is important. So the physics behind working of diodes you already know, okay. I'm just going to give you a brief on how does it work, okay. Now in this elements, we production different colors in the visible range is possible. And the visible, let's extend this visible. And what are these light colors that we already know? One is red, yellow, green. Okay, so RGB is basically something which are called as the primary color. Okay, and apart from that, the orange and blue are also quite popular. Okay, so let me just take that. So if we just look into the primary colors, because of which white LED is possible, it should be RGB, right? So that is something important. So red, okay, G is green, and B is blue. Okay, and if you combine red and green, we can also get yellow color. Okay, so but then RGB is important. Once we have RGB, we can actually vary them, okay, with the primary colors, and then we actually can get any kind of color that we actually need. Okay, so if I just take maybe an example, okay, maybe I can take an example here, and so as an example, if we take gallium arsenide, okay, we actually can take gallium arsenide. It will basically produce red light. Okay, so if you have a red light LED, you are sure that more or less the important component is gallium and arsenide. Okay, and then if you take gallium phosphide, okay, so chances are that we are actually going to get green light. So once we red and green, you can actually combine them, or you can actually flavor the lights very fast. So the combination of them will give the call as the yellow light. It just the theory. I think short of and you can make sense of it. It's not very difficult. It's very simple. We already know about it. Okay. I'll just write down a few points here. Okay. The first thing is points. Okay. So points. Okay. I will just write this. Write sentences in exam. Okay. So write sentences in exam is something that I'd like to suggest you. Okay. So what happens is the first thing is it is forward biased. Okay, the first thing is we have to have it in forward bias. Okay, and the next thing is what happens in the case of diode when it is forward biased. Okay, for this maybe we can just draw a simple illustration. Okay, that will be very simple for all of us. Okay, you can actually have a PN junction here. Okay, and then it's a forward bias, so we know that more or less the depletion layer is going to be very thin. Okay, and then let's say this is the P type. Okay, so we have it here. Okay, so I'll just say this is P, this is N, this is P, this is N, and depending on how strong voltage we are applying, depending on that we actually design the cells, right? So in general this will be actually our P type. Okay, and then this will be our N type, right? So this is what is happening here. But then what happens is if you're considering the P type to N type or N type to P type, we basically have the electrons traveling from one end to the other end. Okay, and then we already have some holes on the other side, right? So this is the basic idea here, that what we do is we can actually just have some, maybe I can draw this here. Okay, we have holes here. So P type, we have holes and it's forward bias, and then we have got electrons here, right? So in the process of crossing the junction, the chances are there this electron will actually interact with the hole. And as it interacts with the hole, we are going to get some kind of radiation coming out of it. Now, if we just consider something like silicon or germanium, the interact after the interaction, most of the energy is lost in the form of heat. Okay, but then here the energy is lost. Some heat is generated definitely, but then there is also some kind of electromagnetic radiation that is coming out. Okay, so we'll be actually getting it in the visible range. So this is exactly how an LED works. Okay, and that is the basic theory that is taking place here. Okay, so what we can write down the some important points here is this. Okay, so maybe you can just continue with this. Number two, okay, the electrons from N type, okay, material, okay, process and recombine, okay, and recombine with the P type materials. Okay, so we basically have this. Okay, and then what happens is when recombination takes place, because of recombination, we can say because of recombination, okay, we have the electrons releasing energy in the form of heat and light. Okay, because of recombination, energy is released in the form of heat and light. So, we are interested more in the light part and not in the heat part. Okay. So if we consider something like germanium or silicon, most of the part is heat. Okay. So you basically have in the form of heat. Okay. Most of the released energy is heat. Okay. But when we are considering something like LED material, okay, uh, light is the okay. So light is the significant part. Significant part. Okay. So if you want just to write down a very normal standard theory for this, I think this is okay. Okay, this should work. Okay, this much part is fine for writing down the theory. But then please explain it properly. Okay, that's very important. Okay. Just maybe delete this part. Okay. And then what happens here is usually that what we can do is we can actually plot a graph. Okay, and then I think I wanted to plot it here only, so I'll just adjust it so that I can just plot it here somewhere. Okay. So what happens is usually that our interest lies in how much energy is getting radiated. Okay. So what you can do is you can actually plot a graph. Okay, between the radiated light. Okay. So on one side I might write down. Okay. Space radiated light, okay, or radiated light, let's say I'll write it down in milliwatt. Okay, you know, the radiated energy that is being done basically a normal LED is nothing but in the form in milliwatts. Okay, it's not that it has got a very large power. Okay, it doesn't generate that much of power, but then this milliwatt intensity is actually good for actually visualizing the red light or the blue light or the green light. Okay, and on one side we can actually have the current. Okay, and the current that is being generated in the circuit is in milliamperes. Okay, so current we actually have it in the form of milliampere. A milliampere current is getting generated. Okay, so if you actually plot this graph, what you're going to get is basically a straight line. So it simply implies that more current and the intensity of light will be more, and that will actually increase linearly. So as you keep on increasing the current, the intensity of light will be more. What do I exactly mean by increasing the intensity of current? It means that more number of electrons will actually recombine with the holes. Okay, so more current. Okay, we have got more intensity. Okay, and okay, and that is important. And the relation is linear. Okay, current, or I can write down I versus power. Okay, power, it is linear. Okay, intensity versus power is basically linear. So this is important, and I think whatever I've written here in this particular slide is actually going to explain a lot of things. Okay, so let me just adjust it. Yeah, so this is important. Okay, and then what happens is usually there are different kinds of LEDs that are actually present. Okay, but then it is important to know the LED voltage and current. Okay, so let's just draw one circuit to understand the importance of LED voltage and current. Okay, so I'll just give you one simple idea here, and then I'm also going to explain the a problem. Okay, we'll probably take a numerical. Just do it. Okay, on here only. It's very simple. So it's LED voltage and current. Okay, so let's just draw this figure. Okay, so you know, whenever you have basically an LED, you cannot just simply connect it across the voltage power supply. Imagine a 12-volt power supply actually being used to actually light up an LED. What will happen immediately? The LED will get damaged. Okay, because the rating is not that much. If we apply 12 volt, too much current is going to flow, as a result of which enormous it is going to get generated, and because of which the LED will usually get damaged. So in a practical circuit, we usually don't use LED alone. Okay, we basically connect it with a resistor. So if you look into our circuits that we are going to study in transistors and all, we'll see that we are going to use a lot of resistors and all, because you know this is important. Okay, so what I can do is probably I can just draw a resistor here. Okay, resistor. So when I'm doing it freehand, it doesn't, somehow the diagram is not good. Anyway, so I have my resistor here. Okay, so let me say that this is the load resistance. Okay, or we can also write it down as the RS, so series resistance. Okay, this is there, and then we actually have got the current flowing across it. Okay, so this is IF. Okay, so we are having a musical class. Please ignore the music behind. Okay, as I'm somewhere where the music is being played. Okay, so this is the voltage that we have. Okay, so this is Vs, let's say, and then we have got the diode. So you know, this particular point Vs will actually generate a voltage. Okay, and then there will be some kind of voltage drop, or the voltage drop across the diode, LED, light emitting diode. Okay, so whenever I'm drawing this circuit, if I'm drawing it LED, these two arrows are also important. So I've drawn that. Okay, so I've got two voltage drops here. Okay, so maybe we can just write it down. Okay, so we have got Vs. Okay, and then we have got VD. So maybe we can just write down some points. Okay, so let's write down what is our Vs. Okay, so you know, this is nothing but the forward bias voltage. Okay, so the input voltage we can say. So let's just write down this input voltage. Voltage. Okay, and then this VD is voltage across LED. Voltage across LED. Okay, so we have the voltage across LED and the input voltage. And what we do usually is that when we are having actually these two voltages, we know what is the voltage drop across the resistor. Okay, so I'll just write that part. Okay, but before that, I think I should just write down some important points here. So forward voltage rating. So how much forward voltage should be applied in a typical LED? Okay, so forward voltage rating. Okay, voltage ratings. So the forward voltage rating would be 1 volt to 3 volt. It is important, forward voltage rating. And for this particular voltage, how much current we are going to get is forward current. Okay? Forward current that we are going to get is approximately 20 milliampere to 100 milliampere. Okay, so these two voltage ratings are important. So if you apply a voltage of, let's say, 3 volt, the chances are you can actually get forward current up to 100 milliamperes. Okay, so if something exceeds this voltage, the chances are that the voltage will basically, or the LED will basically get destroyed. Okay, so that is important. So if we just want to find out what is the voltage across RS, okay, so let me just write down this. This is the formula that we are going to work on. Okay, so I'll just write down a separate here. Voltage across RS. So that is the voltage across the resistance. So what I will do is I just write down probably RS is equal to, okay, just write it down here. So just consider it to be the subscript. Okay, so voltage across RS, what will be the voltage across RS? So I'm considering the voltage across this part. Okay, so the voltage across this part would be nothing but the voltage of the battery minus the voltage drop across the diode. Okay, so we can just take it to be Vs minus Vd. Vs minus Vd. Okay, so this is the voltage across the diode. This way, just hanged. So we have got Vs minus Vd. So if I want to just find out what is the current in the circuit, okay, I can simply just find out the current across the resistor also. Okay, so current uh, uh, across the circuit. Okay, current circuit current, or we can say this. So we basically have it here. So I'm just going to use freehand here. Okay, so the circuit current is basically, let's say I write it down as I. Okay, F stands for forward. Okay, should not be confused here. And this is Vs minus Vd. Okay, and divided by Rs. Okay, so I'll just let's take up a question. Okay, what kind of question might be there for this normal LED? Okay, I'll just give an example here, and then all of you can just do the calculations. Okay, it's very simple. So let's say you can let me take down this question. Okay, what value of series resistor is required to limit the current? Okay, sorry, did not get right. What value of series resistance is required to limit, okay, the current through, okay, LED to 20 milliampere, okay, with a forward voltage drop, okay, of 1.6 volt when connected to a 10 volt supply. Okay, so you basically have a battery and you are actually connecting it, and then the battery has got a supply of 10 volt. Okay, and then the voltage drop across the LED is given, and then you're basically going to just find out what is the current or what is the value of the series resistance. Okay, so what we can do is we can use this formula, and this is very simple. Okay, and then if we just calculate it, okay, I'm not going to calculate it because I think it's very trivial. Okay, very simple. The answer that you should get is around 420 ohm. 420 ohm. Okay, so why exactly did I write this problem when I am discussing this value? Okay, because you're considering a current and voltage in the range of milliamperes and volts, 1 volt or 2 volts, okay? But the resistance that you connect is 420 ampere ohms, okay? So if we just use the simple ohms law, we know that this much resistance is required, okay, to more or less restrict the flow of current, okay, so that the LED is not damaged, okay. So many devices do use these actually in the range of kilo ohms also. So typically, in order to safeguard an LED, the typical range of LEDs that we should actually, typical range of resistance that we actually should use is nothing but in the range of kilo ohms, okay. So that is very important. So I think advantages of LED is very obvious now. We have it, okay. Advantages of LED, okay. So advantages of LED. So what happens in the advantages? Let me just write down this. First point is low voltage. So a major challenge across the world is actually conservation of energy. We need to save more and more energy. That's very important. And if we are using devices which actually eats up a lot of power, we cannot say that we are actually in the right way, right? But then something like LED actually consumes such a less power. Imagine in old days, okay, you might not even some of you might not have seen a CRT TV, okay, cathode ray tube TV, okay. Those actually has got those cathode ray tubes which actually requires a lot of energy to work, and based on which people are going to watch television. So even your television bill would have been very high. But nowadays, you are getting those televisions which are actually 5-star rated, energy efficient, marks are given, okay, on that, okay. So these are all authorized. So basically, they have got a very good low power consumption capacity, okay. So basically, it works with even lowest of voltages, okay. And then apart, because it works on lower voltage, basically it will have definitely some longer life, because if you supply more power, you need more voltage to run a device, more heat will be generated, and that heat slowly but surely affects the wear and tear of your mechanical device, right? So if it's an electronic circuit and more heat is generated, the device is going to get damaged very soon. Imagine a normal laptop that you basically use, okay? So if you're using basically a normal old processor, okay, let's say even nowadays, even if you use i3 also, and if you're doing some heavy work, what happens is the CPU is going to generate a lot of heat because of the processing system, and that heat actually affects the circuit, and based on which we don't have a longer lifetime of that particular circuit, right? But when you use an i5 or an i7 processor, it basically has got more processing speed, okay. So that means whatever work is done at lesser consumption of power, okay, and at a higher efficient rate, okay. So that is why, like, what happens is if we have a LED, it basically has a longer life, okay, usually 20 years. Usually. So I'm not saying that everything will have, it might not have a television running for 20 years, might not be possible. But then in general, LEDs usually last on their own for 20 years, okay? And then fast on off. So, when you have a circuit or when you have a device which has got an LED attached to it, based on which you can say whether it is on or off. As soon as you switch off the circuit, it switches off, okay? And as soon as you basically switch it on, you see that the LED straight away glows, okay. So it has got a very fast response. That is very important, okay. One more thing I'd like to tell you, I think this is something which is a bit unusual, which we usually don't study, is multicolor LED. Multicolor LEDs, okay. So what happens is some LEDs will actually emit different colors, okay. So it's not that we have got two different LEDs together. Here we actually have two diodes being connected, okay. So when they are connected, the two actually keeps on switching on and off regularly, because of which a third color can also be seen, okay. That is also possible. Or in general, we can say LED emits one color, emits one color when forward bias, okay. It will emit one color when it is forward bias, okay, and another color when reverse biased, okay, when reverse biased, okay. And this is basically a multicolor LED. Now why does it, how does it work? An LED usually does not work in reverse bias, or if you want to safeguard an LED from the reverse bias current, you can just connect another additional diode. So basically we are working only in the forward bias. So what happens in this typical multicolor LED, there are two LEDs which are being connected, okay. So if I just consider two LEDs here, one will be connected in forward bias, okay. So one will be like this, maybe, okay, and the other LED will be like this. It will be in the other direction, okay. So they are connected in parallel to each other, okay. And then you can actually apply the biasing. So when you apply the biasing at one time, at one point, one biasing will be for one LED which will be in forward bias, and for the other it will be reverse bias, so the other LED is not going to work. Okay, but when you actually reverse the bias, the LED which did not work before is going to work now. Okay. So this is a typical circuit of multicolor LED. You have got two LEDs which are getting connected. Okay, so this is important, and then I think I missed out the arrow. Very important. So you can
Sir,
make this. Yeah.
is the defined colors depends on the applying potential, sir?
No. The different color depends basically on the element out of which it is made. Okay. So if you just look into today's class, I told you that if you use gallium phosphide, you're going to get a green light. If you're using gallium arsenide, you're going to get red light. Okay. So yes, we had this intention that, okay, if I take imagine you are taking a red LED and you are applying voltage. If you keep on changing the voltage, you will not get any other color. It's going to be red only. Only the intensity is going to change. And that is why this graph, okay, that is why this graph, you see, with voltage, the intensity will change, not the color. Very good question. Yeah, I must say this is important. When we change the voltage, the intensity changes. So we have a change in intensity, but not the color. So a very basic question is, on what does the color depend? It depends on what material it is made of. Okay? So that is very important. So if I have two LEDs, let's say this is emitting green and this is emitting red, these two LEDs will actually be made up of different semiconductor material. One might be gallium arsenide, the other will be gallium phosphide. And that is how they are combined. And I think that is the beauty of science, that we are actually going to use different ideas and combine different things together, so that we are actually going to get a similar output. Okay, so somehow the free end doesn't go that well. So this is exactly how a circuit will look like. And usually when you actually show it in a diagram, you basically do it this way, right? So you basically say you are applying a positive voltage V. Okay, and then we have got the current IF flowing along this direction. So, you can actually make the entire circuit, but anyway, one side we are actually earthing it because we want to maintain the potential. So this will be your IF. So forward bias. So, if you're connecting a circuit, and let's say it's a forward bias current that is flowing, and let's say this is a diode and this side is N side. Okay. And then if the potential is applied positive, this will be in reverse bias now. This will be in forward bias. So this will work. And this will emit the light. And this won't emit the light because it is in reverse bias. Less number of charge carriers, no recombination as such, minimum amount of heat generated. So it's fine. As soon as we make a negative potential, we reverse the biasing. We basically have this one as forward bias and this will become reverse bias. So this won't work and this will start working. Okay. Now what we do is, imagine I'm doing it very fast. So I'm switching to plus V to minus V, plus V to minus V very fast. What will happen is both of these lights will be actually coming out. And then if it's red and green, probably we'll get a yellow light out of it. So these two LEDs can give rise to a third color, which is also possible. Okay. One more basic thing I'd like to tell you is that, uh, blue LEDs and white LEDs are usually costly. So the LEDs which are being used at your home, and if you go for purchasing one, okay, you have to spend around 150 to 200 rupees, because if you're just purchasing a normal white LED, maybe not a non-branded one. Okay, if you're going for a branded one, it might go up to 300, 400 rupees. Okay, nowadays those even smart LEDs are available, which you can connect with your smart speaker, and then you can give a voice command to change the color of that LED. Okay, so how do you think it works? It works on the simple idea that when you give a command, okay, it sends a signal, and the system understands that which LED should be forward biased, and that is forward biased. And as soon as you get that forward bias, you get a green light coming out of it. Okay, if you want white LED, there was all of these will actually come out, keep on flickering, and all of them will combine, will give you the RGB combined, will give you the white color. Okay, so this is exactly how an LED works. And why blue and white is more financially more costly? Because the reason is, it's more difficult. The material with which they are made up of are more costly, the raw material, and that is the reason. Initially it was very difficult to get blue light out of the system, because whenever the electron combines with hole, certain specific energy in the visible range will be given out, the photons. Okay, and mostly it was seen that if we don't do that band gap engineering, or if we don't consider the material, it's simple. Okay, it's simple. The idea is simple here. What happens here is this. Okay, you have the electrons here and you have the holes here. Okay, and as soon as we have the electrons, here, it gets de-excited. And as soon as it gets de-excited, we say that they are recombining. Okay, that means they are coming back to the holes. Okay, they are recombining, or they are occupying the position which are vacant here. Okay, as soon as they come out, you are going to get a emission of radiation. Now this emission of radiation might be red or green, RG, but blue was a bit difficult because it took some time to find out a material which will have a appropriate band gap, so that the energy difference between these two band gaps lies in the wavelength range of blue light. Okay, so that is why actually it took some time. That is why it takes some time, okay, to actually get a white light. So that is very important. Okay, so what happens usually is that this band gap engineering took some time, and then there was a scientist, okay, from Japan, who actually got the Nobel Prize for getting this blue light done. Okay, and then once we had the blue light, all these three colors were combined to actually give you the white LED. I actually have a very short video. Once I was very lucky to actually listen to his lecture when I was in China. Okay, I listened to his lecture. I will actually share that video with you. Okay, he's actually now an entrepreneur. He is actually having a company in his own name. Okay, but he's a Nobel laureate. Okay, what is the Nobel Prize based on this? Okay, so this is what is all about LED. Okay, and then I think we cannot just talk without the application part. I think applications, there are many. You can actually do a bit of study on your own on what are the applications, but then most common is basically as a power indicator, which we actually observe in our day-to-day life. Okay, and what about one more application? Let me say 7-segment display. Okay, 7-segment display. So I'll just give you this as a homework, why we basically call it as a 7-segment display. You can Google it, but I'll just give you a basic idea that if you go to any outlet, let's say you go to a KFC where there is a display machine which writes the number when your order is ready, or you go to a hospital where basically the token number is displayed on the screen, okay, on an LED screen, or you basically go to a bank where it just displays ting tong number 5, something like that, and you see that 5 is displayed. Those are all nothing but LED segments. Okay, these are 7-segment display, because using these 7 segments you basically can make a number from 0 to 9. Okay, so these are actually separately made. Suppose 90 or 95, then one is a 7-segment display which displays 9, and another second segment display will actually display 5. Okay, so you can just go through this, how does a 7-segment display work. Okay, and you will understand it. So this is a very simple idea. Okay, so I think this is the last
Sir,
class for yeah.
sir, is it like the calculator shows the in the displays?
Yes, right. So what happens usually is, even in a calculator also we are having that. Okay, the signal flows, and then we are actually having some kind of display. That is also a 7-segment display kind type. Okay, so I'll just leave it to you to actually just explore it a bit more. Okay, but then obviously I'm not going to ask much question on this. But what happens in a 7-segment display is there are 7 LEDs which are actually connected. Okay, so there is already a circuit which is there. You can always Google it and find it out. Okay, so this is important. Maybe I can just show it to you once if I have it here. Okay, if the net is fast, and then I can just 7 segment display. Okay, 7-segment display. So let me just go for the images here. So you see, this is the display that I'm talking about here. Okay, so we just go for the images. If you just do it, okay, you're probably going to get it. Okay, I hope it opens. Yeah. So this is basically a 7-segment display. Okay, so you see 1 A B C D 4. Okay, E F G 7. So there are 7 segments. So this is on, this is on, this is on, this is on, this is on. You get 3, and then that means F and D should be off. Okay, so this is exactly how an LED works. So see, this is the basic circuit. Okay, if you just look, I think this is better. This is better. Yeah, so you can look into this. Okay, so nowadays everything is so smart that you can actually apply a power according to your own will. So if I just apply some power, and then I know that I can use a switch here, then might be this will work, this will be off, this will work, this will be off. Okay, so it is designed in such a way, as a result of which you are actually going to get that LED output. So that is actually a very good application of LED. Okay, and this has actually this LED, the device, the diode LED, because of which we are actually having so much of less power consumption nowadays, and it is very much energy efficient. Okay.